video, we're going to go through some fun math where we can look at a problem three different ways. I want to look at a taxation problem first graphically using supply and demand, and then we're going to do it numerically, solving some equations, and then we're going to look at the same problem analytically, where instead of putting in numbers and looking at a specific line for supply and demand, we're going to look at the general solution for any equation of a line that represents demand and supply. Now, of course, this general solution is not going to really be that general because we're still going to be assuming that the supply curve is a straight line function and demand curve is a straight line function, which in the real world is just not true. But let's assume that we're going to learn some interesting lessons nonetheless. Some interesting things are going to pop out of these equations, especially when we get to the end and we look at the analytical solutions. We'll learn some general rules for working with problems whenever we have straight line demand and supply curves. Now, this is an example that I created for a test that I gave a couple of days ago, and during the test I decided to do some math regarding these lines and have some fun with it. So I just thought I would share with you what I did. What this fake little example is pretending to be about is about marijuana legalization. Now, in the United States, there are many states that have begun legalizing marijuana, but since it's a drug, it's going to be regulated and it's also going to be probably taxed. And this is kind of similar to how we treat alcohol in the United States, but every different state treats it a little bit differently. Now, the state I am in, North Carolina, all of the liquor stores, now by liquor I mean distilled spirits like vodka or rum or whiskey or things like that, all of those things with higher concentrations of alcohol are sold by stores that are heavily regulated by the North Carolina Alcoholic Beverage Control, or ABC Commission. They say that they have three goals, and their three goals are control, service, and revenue. And here's a different logo of the North Carolina Association of ABC Boards. Basically, different counties and cities have oversight boards that actually run the ABC or the liquor stores in North Carolina. And you see the same logo and motto: control, service, and revenue. So they have two opposing kind of goals. The first is that they want to control the consumption of liquor, which means they don't want people drinking too much and getting drunk all the time. But then, on the other hand, they want to sell a lot of liquor so that they bring in revenue. And so I was thinking, hey, what if we legalized marijuana and we wanted to put a tax on marijuana? Let's explore some of the impacts of putting a tax on this market. So first, let's analyze this problem graphically. So here I have a demand and supply curve, and the supply curve has a y-intercept of 40, and it has a slope of 0.1. So that means that each time we go up 10, we go over 100, up 10 over 100, so the slope is positive 0.1. And this demand curve has a y-intercept of 200 and a slope of minus 0.1. So every time we go over 100, we go down 10. Over 100, down 10. So that ratio of rise over run is 0.1. And so if we were to do a graphical analysis of this problem, then we would say, okay, well, without a tax, here's the equilibrium. The equilibrium quantity would be 800 units, and the equilibrium price would be $120 over here. But now let's put a tax on the product. And in this test question, I gave the students various tax levels to look at, and they were supposed to tell me how much tax revenue was collected and how much this tax decreased consumption. Whenever you have a tax, the easiest way to do it is to add that tax into the supply curve here. And let's suppose we wanted to look at a $40 tax. Then what you do is you add in the $40 tax into the y-intercept of the supply curve here, So this is the supply curve, which represents the marginal cost of producing each additional unit plus that tax, and we chose a tax of $40. What we do is we can read off what the new equilibrium looks like. So the new equilibrium price looks like it would be $140. The new equilibrium quantity looks like it would be 600 units. So one reason for these taxes is to reduce the consumption of things like cigarettes or alcohol, or in this case marijuana. So this would decrease the consumption by 200 units. Remember that tax, we add the $40 into the y-intercept here, and the reason is that the supply curve tells us the marginal cost, the additional cost of producing one more unit of the good. Well, after the tax, we're assuming this tax is paid by the business, although it really doesn't matter. But if the tax is paid by the business, now the marginal cost is the additional cost of producing the actual good itself plus $40. So all we're doing is we're adding in $40 to each point, right? So $10, $20, $30, $40 everywhere. $10, $20, $30, $40. So that's how we're analyzing this tax. Now don't worry, if you're getting bored, I'm going to speed this up if you already understand the taxation idea, but I just want to make sure that people who haven't seen this in a while are on board. Now, with a tax, there are actually kind of two prices. In this case, there would be a price that the consumer pays, which would be $140. But then if we go down 40, 1, 2, 3, 4, down $40, there's another price, and this other price is the price that is going to be received by the business after they pay this $40 per unit tax to the government. And so the consumers pay $140, the businesses receive only $100, and so you can visualize how much tax revenue there will be collected by a rectangle. And this rectangle is going to be, and we could calculate the total tax revenue here as $40 per unit, so that we call that T, times how many units are being sold, 600, so that's times Q, and that's going to give us the total amount of tax revenue collected. And looks like that's going to be $24,000 in this case. And we can visualize that as a rectangle again right here. The area of that rectangle is the amount of the tax that's going to be collected. So now that we've done this problem graphically to visualize what would happen with a $40 tax, let's do this problem numerically. So let's look at the equations and solve those. So here we have the demand equation. Actually, the inverse demand equation is the way we graph it. We call it the inverse demand because it's P as a function of Q. But we can write that demand function two different ways, and sometimes one way is more convenient than the other. So here the inverse demand is 200, the y-intercept, minus 0.1 times Q. And if we solve that inverse demand function for Q, then we get the demand function. Demand tells us how much, what quantity will be demanded at each price. And we end up with 2,000 minus 10p. And we can kind of see that equation, Q equals 2,000 minus 10p, by going back to our graph. The 2,000 is the x-intercept. If we plug in $0 for price, then we get 2,000 down here. And that slope, 10, is telling us that the ratio between as we increase P, how much does Q go down for each increase of 1 unit of price, we see that we're going down 100 Q for each 10 increase in price, so that rate is 10. So going down 10 units for each $1 increase in the price. And similarly for supply here, we have the inverse supply equation, 40 plus 0.1 Q. If you solve that for the supply equation, we get minus 400 plus 10p. And if we wanted to solve for the equilibrium without the tax, then we could just set the right-hand sides, right? Let's just do the equilibrium quantity here. Set these two equal to each other and see what that equilibrium quantity is. And so that's what we have right here. And just take a second to solve that. Subtract 40 from both sides, and we get 160 equals, and then we add 0.1q to both sides, equals 0.2q. Divide both sides by 0.2, and we're going to get that equilibrium quantity of 800 units. And then we could take that 800 and plug it back into any of these equations, back into that one or back into that one, and that would tell us what the equilibrium price is. Easy enough, right? How would we do this numerically using these example equations if we wanted to add in a tax of $40? Well, what we do is we just take the inverse demand and we do what we did in the graph. And what we did in the graph is we took that supply equation there and we added into the y-intercept $40, right? That's the tax. So we could call it $40, or we could call it T if we just wanted to look at any level of tax, which we'll do in a minute. And so that gives us the equation P equals 80 plus 0.1q. And then if we wanted to solve for the equilibrium quantity to see how much that tax is going to decrease the quantity that's going to be exchanged in this market, we could take that equation, including the tax, that supply equation, and set it equal to this demand equation, which has not changed. And then, of course, we're going to get the same answer that we did in the graph, which is that the equilibrium quantity now with the tax is only going to be 600. And then we could plug it back into any of the other equations, and depending on which equation we plug it into, whether we plug it into this demand curve or this old supply curve without the tax or this one with the tax, we're going to get one of those two different prices that I was telling you about. So again, the two prices are $140 with the tax and $100 not including the tax. And we can see by looking at the graph which we would get by plugging into which of the equations. So we would get the $140 answer if we either plugged it into the supply equation with the tax or the demand equation. But if we plug it into the old supply equation without the tax, then we would get $100, the amount without the tax. Okay? Now this leads me into the interesting part. The interesting part is I asked myself, I wonder if we had a market like this, what tax level would it be that maximized the tax revenue? So suppose instead of the logo just being control, service, and revenue, suppose it was just revenue. That's all you cared about was we want to sell marijuana and we want to get the highest tax revenue possible. I wondered to myself, well, how big of a tax would you want to set to maximize the tax revenue? So let's look at that. So how we're going to change up what we're looking at here is instead of adding in a particular value for a tax like $40, we just want to add in a general level of a tax plus, and we could call it T, the letter T here. And what that's going to let us do is see how various levels of tax affect the equilibrium price and the equilibrium quantity. Once we know the equilibrium price and the quantity, we can see how do we maximize the tax revenue. And again, how do we calculate tax revenue? Well, tax revenue is going to be the tax level T times the quantity sold. So if we can figure out a way to build all this into an equation, and then we're going to use very simple calculus, we can figure out what tax level would give us the biggest tax revenue. So let's get started here. So if we wanted to solve this equation here for the equilibrium quantity, and equilibrium quantity is something we're going to want to know because we're going to be multiplying that times T in order to figure out the level of the tax revenue, then what we want to do is just over here add the T, right? Because that's what we have in this supply equation. When there's a tax added on the producer, we have to add in that T. And so that just changes the equations we need to solve to these two. So let's go through and solve those equations and see what this function for Q is going to be. We want to do kind of the same thing we did before, right? We want to subtract 40 from both sides, and we want to end up with 160 over here. And then we want to add 0.1 Q to both sides. And so we're going to end up with plus 0.2 Q on the right-hand side. And now we've got this extra term T. Now, if we're solving this for Q, let's go ahead and subtract T from both sides. We're going to end up with minus T on this left-hand side equals 0.2 Q. Solve this equation by dividing everything by 0.2. And just like we saw before, what we're going to end up with is 160 divided by 0.2 is equal to 800 minus T divided by 0.2. 1 divided by 0.2 is 5, so we're going to end up with 800 minus 5t equals Q. So the quantity that's going to be purchased is 800 units, which was our equilibrium quantity without a tax, but we see that the quantity people buy is going to go down by 5 units for every $1 of tax that we add. Well, that's pretty interesting. The goal here is to figure out what tax level will maximize the tax revenue. So that's where we bring down this idea that tax revenue is just T times Q. So let's use that idea. Now that we have an expression for Q as a function of T, what we can do is say, well, tax revenue is T times this expression for Q. So T times 800 minus 5T. And that is tax revenue, T times Q. So let's call that TR, although, TR usually sounds like it would be total revenue, but let's just say TR for tax revenue here, right? And if we multiplied that through, we get that tax revenue equals 800T minus 5T squared. Gorgeous. All right, now how do we maximize something? Well, we're going to have to use calculus, but calculus is easy, especially if all you have is a polynomial here. So if we want to maximize this, then we see that this is a quadratic equation, and quadratic equation is going to have the shape of a parabola, and a parabola is either going to be like this, it's going to be convex, or it's going to be like this, it's going to be concave. And in this case, it's going to be concave. It's going to have a maximum. And what we want to do is find at what tax level do we have that maximum tax revenue. A derivative tells us the slope. And what we're looking for is to find where is the slope 0. Where are we at the top of that parabola? So here's what we're going to do. We're going to take the derivative of total revenue with respect, the partial derivative with respect to T. So here what we're saying is we're going to choose T. We're going to adjust T. Here I changed this graph just a little bit so get a better view. We're going to change T until we see for what value of T, for what tax rate per unit, can we find a place where it is flat and therefore the tax revenue on the y-axis is maximized. So taking the derivative of 800t with respect to t is just going to be 800. And then the derivative of minus 5t squared with respect to t is minus 10t. We're looking to see where that derivative, that slope of the tax revenue function, is equal to 0. And we are going to get that t equals 800 divided by 10, or $80. So that tells us that if we tax each unit of marijuana by $80 each, then we will have the maximum tax revenue. All right, well, let's look at the graph and see if that appears to be a right answer. So let's take this line, including the tax, and let's start off at 40, and let's add in 80 to the y-intercept. So we're going up to 120 here. And it looks like here that the equilibrium quantity would be 400 units, and the equilibrium price paid by consumers would be 160, with half of that money going to the government as tax revenue. So here's the amount of the tax, that $80, and $80 times 400 units. This green rectangle is going to be our tax revenue visualized. And so it looks like our tax revenue is going to be 400 times $80, or $32,000. And yeah, that tax revenue is bigger than what we were getting with a tax level of $40. tax level of $80 per unit does give us a bigger tax revenue. Interesting. Let's just verify this using our equations here. So if the tax level is $80, then we can go back, plug that in to our equations over here. Instead of a general T, we could plug in $80, and we could solve those equations just like we did before, and we could verify everything that we just found out. I'll leave that as an exercise. All right, so now is the interesting thing that I really want to get to. This is the oddly satisfying part. What happens if instead of looking at just one particular example of a linear demand and one particular example of a linear supply, what if we were to say, well, in general, we could have a demand curve that looks like A is the y-intercept minus B is the slope times Q. And then if you solve that, if you needed the Q equals version of the function, then it's going to look like this, A over B minus 1 over BP. And a general supply function where the y-intercept is C plus a slope D times Q. And if we solve those two equations for two unknowns, leaving everything as a variable, so we solve the right-hand side set equal to each other here, then in general, you're always going to get A minus C. What's the difference in the y-intercepts on the numerator, and then the slopes added together in the denominator. Now again, since I have this written as minus b here, this is going to be the positive value of the slope here. Check that out with the example that we did over here, the particular example, just to make sure it works. So Q equals A minus C. Well, we have 200 minus 40 on the top. And then we have the slopes added together, but we're going to make the minus 0.1 positive. So 0.1 plus 0.1. And what we're going to have here is that 160 divided by 0.2 that we had before, which is 80, right? So it's good to see how to use these equations when you have a particular example of a linear equation. But the oddly satisfying part is what happens when we solve this, including a tax. And let's add in a tax by doing precisely what we did over here on the left-hand side. We're going to add a letter T into supply. So let's go ahead and do that. Plus T. So T is the per unit tax. And let's highlight that. And then now we're going to add that per unit tax into these two equations down here as well. And what happens whenever we solve this is we have an extra term. We have Q equals A minus C over B plus D. Let's just keep that part together so we can compare. So we have a minus the tax level divided by B plus D. Now, yes, I could combine these into one big equation since the denominators on the bottom are common. Personally, I like to picture these as two separate terms. This is the equilibrium quantity with no tax, and this is how the tax rate is going to affect the equilibrium quantity after we put a tax on. Now the equilibrium price, just in case you were wondering, this is what this function is going to look like. And I encourage you, if you're interested in getting better at doing this kind of math and economics, sit down and do these to make sure that you can get the same answers. So that equilibrium price is going to be the same as it was before plus this extra term, T times B divided by B plus D. Now comes the fun part. Now that we have an expression for the equilibrium quantity when we have a tax involved, and we know that tax revenue is the same thing we were looking at before, this T times Q, right? So we're going to do the same kind of expression we did before, except what we're doing now is a little more powerful, a little more general. So tax revenue is the tax level times Q. So we want to multiply that times this equation over here. A minus C over B plus D minus T over B plus D. And what we want to do is the same kind of thing as before, except now we're going to get a general solution. We want to know how high should I set a tax level for any equation of demand that's a line and equation of supply that's represented by a line. How high should this tax level per unit be to get the maximum tax revenue? Again, this tax revenue, it's going to be a parabola, and we want to find where the maximum is. So we're going to take the partial derivative of the tax revenue with respect to the tax level. So what's going to pop out of this equation is just going to be A minus C over B plus D minus 2T over b plus d. And then we're going to set that equal to 0. Again, we set it equal to 0 to find where the maximum is. And then when we solve that for t, what we can do is we can just multiply both sides by b plus d. Because this is 0, the b plus d just goes away. So the optimum tax level does not depend on the slope of the demand function or the supply function. Wow, that's weird. So now we're just left with a minus c minus 2t equals 0. And we're solving this for t. What's the optimal tax level? Call that t star maybe. Equals a minus c over 2. Wow. I mean, wow. Now, if you're not a math nerd and you're not an economics nerd, then you're probably not even watching this. But to see, what does this mean? It's telling us that the optimal tax level is just the y-intercept of the demand function minus the y-intercept of the supply function divided by 2. What does that mean? Well, let's go back and look at our graph of our example here. If you want to maximize tax revenue, take this y-intercept here of $200 and take this y-intercept down here of 40, and we want to figure out the distance between those, and we want to split it in half. So 200 minus 40 is 160. Split that in half, and that gives us that the tax level that will maximize tax revenue is $80. Interesting. So the only thing that matters is the distance between those two y-intercepts. Then we take half of that. That kind of blew me away. Now, I'm not saying that I've invented this result. I'm sure that lots of people have run into this before, and this is some kind of standard result in public finance literature or public finance classes, but I thought it was kind of cool. A nice, simple, elegant result. Now, let's go further, though. Let's go further. Next interesting result. What about the equilibrium quantity? What happens to the equilibrium quantity when we put on this optimal tax? Again, this is for any demand and supply, as long as they're a straight line, which isn't realistic in the real world, but okay, fine. So if we take this tax level, T star, and we plug that back into this equation that tells us the quantity based on the tax level, here's what we're going to end up with. The optimal quantity, if you're thinking about it this way. Now, by optimal, I just mean optimal from a tax revenue standpoint. If that's all you care about, then the quantity that's going to result from this tax revenue maximizing tax rate is a minus c over 2 divided by b plus d. Now, that's also fascinating. Compare these two items. This optimal quantity after the tax has been imposed, and the optimal quantity here in equilibrium when there's no tax. A minus c over b plus d. Well, this is the numerator, a minus c, divided by 2. So if you're dividing the numerator by 2, that is exactly the same thing as, we could move the 2 over here, right? A minus c over b plus d times 1/2. So this is telling us that if your goal is to maximize tax revenue, what you want to do is choose whatever tax level cuts the quantity in half. Now again, it would be lovely if in the real world demand and supply curves were perfect lines, and then this would be a wonderful simplistic result for any government that wanted to maximize tax revenue. But for such a simple model, it is wonderful when you're analyzing a question and you get these very, very simple results. So the tax level, take the y-intercept of the demand minus the y-intercept of supply, cut that in half. So basically what you're doing is you are taking the supply curve here, right? Once you add the tax, what you're doing is you are moving this supply curve that has the tax involved halfway, right? You're starting down here at a y-intercept of 40, and what you're trying to do is move it exactly halfway between the y-intercept for the demand and the y-intercept for the supply. Kind of interesting. Now, one other thing, last thing that's kind of oddly satisfying here is one thing we always want to know about a tax is what is the excess burden of the tax, or what is the deadweight loss, right? What can we say about the deadweight loss from a tax when the government is trying to maximize the tax revenue in this simplistic and not real world case when demand and supply are both a straight line? What can we say about that deadweight loss? Here are a couple things we can say. This total surplus triangle here, right? So this is what total surplus is without a tax. That's what we always want to compare back to. We can think about it as this triangle here. Let me just set it up on its end. And the base of this triangle is always going to be A minus C, right? The y-intercept of the demand minus the y-intercept of the supply. So down here we get A minus C, and then the height of this orange total surplus triangle is going to be the equilibrium quantity, so Q. And the area is just going to be 1/2 times A minus C times the equilibrium quantity. Now, again, in equilibrium, we have an expression for that quantity, and it's down here, A minus C over B plus D. All right, so we can just plug that in. Now, why are we doing this? Well, we want to be able to compare how much total surplus is after we put on this tax revenue maximizing tax. So we have an A minus C times an A minus C, so that's an A minus C squared divided by B plus D. So this is an amount of the total surplus before the tax. So what's happening to this total surplus when we put a tax on? Well, we see a couple of things are going to happen. We're going to have a deadweight loss here, and we're going to have some of that total surplus going to tax revenue, and then some of this total surplus will still be consumer surplus and producer surplus. Well, how big are these things going to be in proportion to the original total surplus? Is there something interesting that we can say about that? Well, how big is the tax revenue going to be? Well, let's go back down here where I've done a little bit of algebra. If we just take our T star, our tax level, right, and we multiply that times Q star, we're going to get our tax revenue. So we just take that A minus C over 2 right here, multiply it times this quantity, A minus C over B plus D times 1/2. Okay, that's right here. And we multiply that through. We have a 1/2 here times a 1/2. Well, that gives us a 1/4. And then we have A minus C squared over B plus D. So if we compare this quantity, the tax revenue, to the total surplus without the tax, we see that the tax revenue is going to be half of the total surplus, right? This is a 1/4 A minus C squared over B plus D, and this is 1/2 A minus C squared over B plus D. So the government is going to be able to get half of what used to be the total surplus. And what about this deadweight loss here? Is there a way to figure out how big that is? Let's zoom in on this total surplus triangle. Remember that if the government is maximizing their tax revenue, then what they're doing is they're cutting this quantity in half, right? So we know that this deadweight loss triangle here, right? So we're just taking this little deadweight loss triangle over here, and that's going to be what it looks like on the top of a triangle. I just like visualizing it that way better. Then what is the area of this deadweight loss triangle always going to be? Well, we know the height of the triangle is Q over 2, or half the height of the total triangle. And then we know the base here is going to be the tax level, right? So that base, whenever we look at that deadweight loss, the base of that triangle is always that tax level. So if we take our expression for the tax level, which is A minus C over 2, and we multiply it, so that's our tax level, which is the base of the triangle down here, and we know the height is the original quantity, the original equilibrium quantity, which is A minus C over B plus D, over 2. Then what we're going to end up with as the area of this deadweight loss triangle. So we have the tax rate, A minus C over 2. We have the quantity, but half of that, and that's the height of the deadweight loss triangle. But then since we're finding the area of a triangle, we have to multiply 1/2 times base times height. So we have another half here. And so if we multiply the half times here's another 1/2, we have an 1/8 times a minus c squared over b plus d. So what this is telling us is that if we look at this total surplus to begin with, we're beginning to see how this total surplus is going to be split. A half of it is going to be captured in tax revenue. This 1/8 a minus c squared over b plus d is 1/4 of the total surplus. So 1/4 goes to deadweight loss. And then that means that the other 1/4 of total surplus is still surplus. It's consumer surplus or producer surplus. If you're still watching, you must appreciate some of this a little bit too. But to me, this is a very elegant and interesting result here, that no matter what the slope of supply or demand or the y-intercepts, we have this interesting result that the tax revenue maximizing tax rate is going to capture half of the total surplus. It's going to create a deadweight loss that is 1/4 of the original total surplus. And then 1/4 of the original total surplus will still be either consumer or producer surplus. Fascinating that you end up with such a simple idea. Now, since we have such simple geometry, it's not that shocking, but it's interesting to be able to grind through some algebra that's not all that tough and see how you can get some more general results to a specific problem of a specific demand, specific supply, and a tax rate. So I hope you've enjoyed coming on this journey a little bit with me. There are probably some other interesting things we could do with this simple per unit tax idea. If you're trying to move your thinking from undergraduate analysis or introductory level analysis of taxes and demand and supply and surplus and deadweight loss, and try to move your thinking a little bit deeper toward analytical solutions, I thought this was a very interesting way to try to get you a little bit of exposure to that kind of problem. So as always, if you like what I'm doing here, please subscribe to the channel. Please give me a thumbs up. I will include a link in the video description so that you can download this little worksheet here so that you can verify the results and you can work on it yourself. And if you come up with any other interesting results or interesting things that you find out of this, or if you have any questions, please post them in the comment section below. This is Dr. Berkey signing out, and I hope you have a great day, and I wish you the best of luck studying your economics. Bye-bye.